Okay, Kakema will record a kind of sessions, problem sessions, working on problems, like the tutorial problems for you later on. And so at this, you have a uh, synchronous sessions to learn how to do some problems from the problem sessions. Okay. All right. So let's continue uh, with a our problems or material. Okay. So the next section, so it's the last section of of the chapter, is what we call numerical integrations. So as let's see, from um, fundamental theorem of calculus, the second, it tells you how to compute definite integral. Definite integral is obtained by, well, you compute first the uh, this one, FDC2. First, you compute uh, indefinite integral. I should say, not indefinite integral. I should say this is the antiderivative from indefinite integral. So using indefinite integral. Okay. And second is compute difference. Okay. So if you find f, capital F is the antiderivative, so this is what you do. Okay. This notation means that you find the difference. F is any antiderivative. Okay. All right. So the problem here is uh, even though it is not all functions has, I would say, explicit antiderivative. Okay. So even though some of, um, in fact, there are a lot of function has no antiderivative. For example, sine x squared or sine x over x. Later on, you see a lot of stuff. Sine x, integral xk. There are a lot. All right. So the thing here is what to do if uh, we know the function is the continuous, but we don't have a antiderivative. Okay, so let's do this one. Say so. Oh yeah, from 0 to 1 sine x squared x. Okay, so what we know is sine x squared is continuous. Why? Because it is a composite of x squared, it's polynomial, continuous, and sine is continuous. Okay, so the composition is continuous. And therefore is integrable. Okay, so supposedly we can find this. Okay, but the thing here, you cannot compute this directly because this has no antiderivative. Use FTC2 says x has no antiderivative. Explicit, I would say. Okay, so somehow you have to find a method how to compute this one. Okay. By the way, just note here, by FTC2, sorry, FTC1, it says that if we have this, sine t squared dt, well, FTC2 says that, well, that's continuous, and this the lower bound is constant, the upper bound is the variable x, and so you get this is x squared. So what it says is that this integral is antiderivative and of sine x squared. So this is not the problem of having no antiderivative, but just because the antiderivative is not explicit. See? So the antiderivative is still in term of integral. So I would say this is all right. So let's do some approximations, because you know that from the beginning, one of the, say, the philosophy of calculus is that if you cannot find the exact thing, then you might try to do some approximations. All right, so let's do approximations. And in this slide, we do approximations. Riemann sum is one of the approximations. For example, Riemann sum are approximations. Okay, so at least we try to find uh, using Riemann sum. Okay, so let's just sine x squared. Later on, we use the sum calculator, using calculator, or use Maple, or we can just use the Excel to compute or approximate. Okay, so let's see. What if we use a square? The picture should looks like this one. sine 1. So that's y equal square value of sine 1 in radiant. Okay. All right. So let's do some Riemann sum. Using Riemann sum, say if we just use say four rectangles, we would have 1/4, 2/4, 3/4. Okay, so n equals 4 in this case. Okay, so let's see. So we use the first one is say one uh, the right one, right Riemann sum. Okay, so that means xi is just 1/n. So we compute the Riemann sum. So the height should be sine of I over n squared, and the delta is 1/n. Sorry, this step by step. This just 1, 2, 3, 4. Sorry, n. Okay, so I over 4 times 1. N. So from I equals 1 to we can replace this 4 by n actually. Okay, so this is the right Riemann sum, and if you compute this, you should get 1/4. Okay, so you compute sine over 16 plus sine of 2/4, 2/4 or 16, right? This is 9/16 sine 1. There. So you can check, plug in a calculator and find the. Okay, so that's all right. So that's an approximations, and you can generalize this any n. Okay, so xn here is I over n. So I is 1, 2, 2n. So in this case, you have okay, so 0. This is n, 2, n, 3, n. Okay, that's and the length of delta is 1/. Here the Riemann sum, right? Riemann sum. N is the 1/n. Okay, and this is a n I over n. Okay, so just get you n over n square and 2 over n square. So okay, and you can program this to your Excel or whatever you like to get this. Okay. If you use the left remands, left remand sum means that the representative is just the xi minus 1. Okay, and therefore the left remand sum gives you 1 over n. You can start with from I equals say 1 till n and minus 1 over n. There. Okay, and then you get this number. Or you can use midpoint. Midpoint I is xi plus xi minus 1. Okay. So you get this with a midpoint, you get yep, 1 over n plus let's see, this is I minus 1, right? Okay, so okay, so that's all the approximation of the integral. Okay, so far?
Yes, sir.
Okay, we'll check with Maple later, but I'll show you the formula for this. Okay, so for example, this is the thing that we cannot compute. Sine x square root of 1 over x to the fourth integral sine x over x. So those are examples where we cannot compute the integral because we don't have an explicit antiderivative. Okay. So this is a formula for the. All right. So let's see. Okay, and I'll give you the all the method for this one. Okay. So first you can use left Riemann sum. The left Riemann sum. Okay, here's the. Okay. So the integral is, this is the delta. Length of the interval divides by n. Okay. So this is the left one. This is xi. Okay. This a plus whatever there. Okay. A times this I minus 1 times delta. This is delta. So xi is A plus, uh, okay, so in this case, um, A minus 1 times delta. So it's just delta x because all the same thing. Okay, so this is the formula. Disregard at the moment what is en. That is the error. Okay, for right Riemann sum, this is the representative. So this is a plus I times delta x. Okay, so delta x is just b minus a over n. Times this. Okay. And this is a midpoint. So what is midpoint? Midpoint is this one. Xi plus xi minus 1, the previous point, and then over 2. So the average midpoint. Okay, so you compute this one. Okay, compute this one, you get this. Okay, and there is a what we call a trapezoidal rule. Okay, all right. Let me just let's check the maple. I have to open this. I should have opened this maple. So what we need here is the calculus. Okay, so have you seen the display yet? I'm sharing this the display of maple.
Yeah, it is shown.
Okay, so check the calculus. Okay, and choose the numerical integrations. Where is that thing? Surface revolution, we would need that later. All right, so let's just use integral. All right, so let's choose this approximate integrations or Riemann sums. Okay. Let's see, not this one screen. The one that is really some. Don't forget to get this one. Just go. Oh, yeah, this one. Okay, let's see. What is this? Yes. Look at where I find this, that integral. Let me check it. This one. Ah, sorry, let me just, we'll do this later. Explain this first about uh, I need to find the apps after this. Okay, I'll find it in during the break. Okay, so you see, there is a call what we call a trapezoidal rule. Okay, okay, what is trapezoidal rule? All right, so you see that the values here is using rectangles. Okay, those rectangles. So Riemann sums using rectangles, but it would be slightly better if we use this trapezoid things. The thing is with trapezoid, it's not rectangle. So you have this one instead. Okay, so you have always trapezoid. Okay, with trapezoidal rule, then we compute something that looks like this one. Say, okay, for each step, what we compute here is that, for example, this is the sample. Okay, so it's xi minus 1, xi. Okay, so we use this the trapezoid here. Okay, so this is a sample. Okay, so this xi minus 1, xi. So the length is delta x. Okay. The length of this one is f of xi. This is f of xi minus 1. Okay, so the area for this is, remember, the area. So the sum of the parallel sides, which is times 1/2 of the base length. Delta x over 2. Okay, so this is what we use the area. Okay, so the sum would be if you sum them up, you would get something. So here's delta x is b minus a over n. Say that's the length. Okay, and xi is this I plus I times delta. So that means I plus okay. So that's the formula. So what we see here is that uh, what we need to compute here is the approximations is just using n trapezoids. The area is this one is p over 2, so that means we take this out, right? And you sum this up. All right, so this is, but when you compute this one, it's like a telescopic thing, because you see that first you have f plus fx1, right? And then fx1 plus fx2, then fx2, fx3, fx3. All right, and in the end you have fx1 plus fxn. All right. So you see this one, this appears twice, this appears twice, this appears twice, this appears twice. Only the first one and the last one appears once. So that means this will just give you two times and this one. Yeah. So we have, this which is A, this is B. Okay. So then without the sigma sum, without the sigma, you would get something like this. A. So f of A, f of 2 of x, 1, 2 of fx, 2, that 2 of fx of 1, before one before the last, and the last one is there. Okay, so this is what we call trapezoidal rule. Okay, and so the approximation of that sign using trapezoidal rule this is, so this is, let's divide it into 4 using this way. N equals 4. Okay, so what we have is length interval is 1. This divides by become 8. We have is this sign. Let's see, that's 0. That's 0. Okay, then 2 sine what we have here 1/4, 1/4. Okay, 1/16. Okay, 2 sine 4/16. Okay, 2 sine 9/16. Okay, and then the last one is this one, sine. Okay, so that's a trapezoidal rule. Okay. Questions so far? All right. Let me get back to this.
Sir, I have a question.
Yes, sure. Go ahead.
So we have many methods to solve limits. Is it ngaruh gak sir kayak for the like
All right. Are you saying that which one is better?
yeah, yes
All
sir.
right. So let's go back to this. This is the one that I would like to describe actually. Okay. And this is the all right. So let me just say the fifth method is called the parabolic rule. N must be even. The rule is something like this. The coefficient is you see that the trapezoid, the rule for coefficient is 1, 2, 2, 2, 2, 2, 2, 2, and last one is 1. All right, as we see that. If that's a parabolic rule, the rule for this is 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, and up with 4, 1. So that must be even. Okay, so I'll tell you the reasons later using just using picture. All right, so then why we have so many methods, okay? Which one is better? We just use the best one then, okay? Okay, and it has to do with what we call always errors, okay? Approximation is better if it has a smaller error, right? Okay, so this is how the error is, the estimation of error, okay? In left Riemann sum, the error is this, okay? In right Riemann sum, the error is this one with the negative sign. The thing is that the C is unknown. C is just sum, but C is unknown. That's the reason why we just estimate the error. We cannot compute the real error, okay, the exact error. If you know the exact error, and then you know the exact value of the integral. Okay. All right. Let's see. Oh, sorry. But midpoint, I would like you to concentrate on this is n. This is just n. But this one is n squared. So imagine that if you divide by, let's say, n equals 10, this just divide by 20. But this one is 2400. Okay, so this makes things the error small. Okay, so in that sense, we can say that, well, midpoint is better than left or Riemann sum. Okay. Let's see trapezoidal rule. Trapezoidal rule is, let's see, this 12n squared. So this is a smaller than more than this one. So the number is, this error is bigger than the midpoint, but it's still square. Okay, so let's see. All right, so this why we need this parabolic rule, even though the rule is kind of, it's more complicated than the others, even though it is not difficult also, but just have to remember this, the 1 4 2 4 2 4 2, and then at the end with the 4. Okay, now you see that.
Yes sir.
M
So
to the 4th. Okay, go ahead.
So, if we were given a question about the integral, the methods that we use is depends on the question itself, yeah.
Depend on the questions, and then usually we give out the this page,
Oh, all right, sir.
so you
Okay.
don't have to memorize the formula or the formula for the error. Okay. So, but
All right,
you
sir.
need to uh, let me find the example. Okay.
Okay, thank
All
you,
right.
sir.
Let's do the example. Okay. Let's do one example for this. I need this. Okay. This is just a exactly what we're trying to do. Integral of sine x squared from 0 to 2. Okay. Using right Riemann sum and 8. A is 0. Okay. B is 2. N is 8. So the length of the delta is 2 divided by 8. So this quarter. Okay, so this Riemann sum. Let's notice this, say approximately. This delta x. Say the first one is 1/4 square, so 1/2. Okay, so add them up together and end up with this. Okay. Yeah, so let's now if you use trapezoidal rule, okay, still the same problems. You get this. So 1/2n, 2n is just 1/8 now, 1/8. All right, so you have eight points here. 1, 2, 3, 4, 5, 6, 7, 8, 9, because you have n points. Okay, 2 n points. All right, let's see. The first one is coefficient 1. The last one also is coefficient 1. Okay. But the things in the between the first and this the last is have coefficient 2. Right? You see this number? 0.79. It's almost 0.8. Here, 0.69. But we believe this is more exact. This is more precise. Okay. If you plug that into the parabolic, let's see, where is that thing? I think. Okay. All right, so let's do the error computations. All right, so left Riemann sum, right Riemann sum, this is the error. Okay, so let's do so let's make comparison. Let me just copy the error formula. Okay. right? Okay, I would like to, let's do this one here. The problem is this. Approximate this integral. A, say, right Riemann sum. B, use the, what we call the midpoint. And C, use the parabolic rule. With the degree so the error should be less than, say, to the, so that's basically, that's a engineering stuff. Now the determine n first. So basically, this is the thing is, okay, so how many terms you need to use to compute, to approximate this integral with these precisions, with a error less than 10 to the fifth, negative 5. Okay, so first determine the n, and then put this approximate according to these precisions. All right. Let's see. We'll do the first one here, and before we take a break, because we need to, for C, it's rather cumbersome to compute. Okay, so right Riemann sum. So here, the problem has, okay, A equals 0, B equals 1, right? This is n, whatever n, we need to find is n. Okay. So the delta must be 1 over n. Okay, delta x. And x I must be 1 of I over n. Okay, so this is what we know. Okay, so let's see here. Using the right Riemann sum, En is just 1 over b, so this is 1 over 2n f prime of c. Okay. Here. One over n. Okay, even I don't cannot memorize the formula, I have to look at the table. So don't worry about this. F prime of c. Okay, for some c in, okay, so that's the thing that we don't know. All right, so let's do some estimations. Okay, let's compute the f x squared. Okay. So let's find the estimate this. So compute this one. Is let's see, sine become cosine, but then you need to multiply by 2x. This the derivative of x squared. Cosine x squared. Okay. Okay, so what we need here is to the absolute value. We don't need the sign. Okay, so just disregard the sign. There. Okay, so we need a bound, an upper bound, for this. Okay. Okay, so this cosine becomes, this is e squared. Okay. All right. We need to find a say an easy upper bound. Of course, we need a cosine 2c. Okay, so that's c 0. So say this is the maximum is less than just c is less. All right, so c is between 0 and 1. Okay, so just take a bigger one. So this is less than 2. Cosine is less than 1. So we say cosine at, so this is still equals. All right, c is less than 1, so 2c is less than 2. That's easy. Cosine is always less than 1. So this is what I will call find an easy bound. So this 2. Okay. All right. So when we compute this, this is less than 1 to n. This is less than 2. Compute this is 1. Okay. So when we require less than 10 to the, or okay, so you can guess what is n. So n must be bigger than there. Okay, that means let's see, 10 to the 5th is let's see, that's 100,000. Okay, so you use 100,000 points to compute the integral with these precisions. Right? So it's long computations, cumbersome. Okay. Is it okay up to this point? So here, then you need to compute to find e squared over the t. And you have this formula, sorry. Just 1 over sine sine I over there. There's a lot of computation because you're summing up 100,000 numbers. Okay, so it's Well, you can do that, but it takes lots of time. All right. Are you with me?
Yes, sir.
Okay. So let's check with let's do one more thing with the midpoint. Oh, that the AN is, sorry, just easier for me just to get this one. Midpoint of Riemann sum is just let's see, that's easier to get this thing. Yeah. Okay. So what we have is this formula. Okay, we need a second derivative. So we compute the second derivative. So f prime double prime c. Okay. First derivative is 2x cosine x squared. So first derivative. So the second derivative is just derivative of 2x is 2 times cosine x squared plus 2x times derivative of cosine, derivative of cosine, which is negative sign. So it's negative. X squared become just derivatives, just 2x. So then we have 4x squared sine. Okay. All right. And then we need to find an upper bound for this. Okay. And how to compute that. As long as we deal with the trig function sine and cosine, that's easy. Okay, so this is cosine. Oh, just replaced by c. Yeah. And that's going to be then 2 cosine. Become, you add them up. Right? This is less than 2, right? Because there's 2 cosine is less than 1. The sine is also less than 1, so this 4c. 4c, all right. Our c is in between 0 and 1. Okay, so just take 1. All right, so this is just 6. That's an upper bound. That's easy to find. All right, so our EN don't care about the sign. This is 1 cube, so this 1. 24n squared times 6. Okay, so that means give you, well, 6 becomes 1/4. Okay, and you would like this to be, okay. So in order to get this one, we need that 4n squared bigger than 10 to the the fifth. Okay, that means n squared is bigger than, divide by 4. Divide by 4, that's 10. 10 to the 4, right? Because it's 10 times 10 to the 4. Okay, so n squared is, must be bigger than, let's see. Take a calculator. What is a square root of 2.5? 16, 1.7,
1.58, sir.
above 8. So just take, let's say that is about what, 100, so 160. Okay, so that's enough to take 160 60 points, and you get this precision. Okay, so and bigger than, say just 160. Okay, so this integral the formula is, let's see, again, the formula is look at that one. Midpoint is no, whatever, this 1 over n over this one. I'm sorry, sure. Yes, 1 over n. So this is a not there. Let me see what 61 terms. 161 terms. This 10 points. At the end is that's the approximations. All right, let's take a break for 5 minutes. I'll prepare the maple. Uh, meanwhile, I prepare the maple and then compute the for the third method, which is a parabolic method. Okay, let's take a break.